All right, let's dive right in. Today, we are getting down to the absolute bedrock of computing. I mean, the most fundamental way we can actually talk to a computer's processor. We're talking about assembly language. You know, that secret language that's running under the hood of basically everything, from your phone to your car. So yeah, let's get into it.
But just stop and think about this for a second. You and I, we have these, complex thoughts, abstract ideas, but a computer processor, it only gets one thing, on or off. That's it, just ones and zeros. So the real question is, how in the world do we bridge that massive, massive gap between our minds and the literal silicon brain of a machine? And this slide just lays it all out, doesn't it? I mean, look, over on the left, you've got something that makes perfect sense to us humans. Simple math. But on the right, that's machine code. That's the only thing a CPU actually gets. And they look nothing alike. It's like two completely different universes. This is the communication problem we've got to solve. Okay, so for our first section, we're going to dive deep into this secret language. We're going to figure out exactly how we can bridge that gap between us and the hardware. So here's the plan. We'll kick things off by really digging into the computer's secret language. Then we'll meet our translator, assembly. After that, we'll get into the grammar of the code, see how that code turns into real commands, and finally, we'll talk about why all this low-level stuff still matters so much today. All right, it's time to meet the hero of our story, the translator. This is the magic bridge that lets us, as humans, get as close as possible to speaking the machine's native tongue. So what exactly is assembly language? Well, think of it like this. It's basically a human-friendly version of machine code. Instead of trying to remember those crazy long strings of ones and zeros, we get to use short, easy-to-remember words. They're called mnemonics, which is just a fancy way of saying memory aids. And what's so cool is how simple the structure of an assembly command really is. You've basically got two parts. First, there's the opcode, which is the verb. It's the action, right? It tells the processor what to do. Then you have the operand. That's the noun. It's the thing you're doing the action to. So it's always just action, thing. Super straightforward. Okay, so we've got the basic sentence structure down. Now let's learn a few words, right? Let's check out the basic vocabulary of the processor. It's grammar, if you will. First things first, and this is probably the most fundamental job of all, just moving data around. I mean, before a processor can do any cool calculations, it has to get all its numbers and information in the right spots. It's kind of like setting the table before you can even think about eating. You got to get organized first. So here are a few of the big ones. Now, the processor has this little workspace, like a temporary scratch pad, called the accumulator. So the load command, that grabs a value from memory and puts it on the scratch pad. Store does the exact opposite. It takes whatever's on the scratch pad and saves it back to memory. And move, well, that's just a simple copy and paste, moving data from one place to another. All right, the table is set. Our data is exactly where it needs to be. Now it's time for the fun part. This is where the processor actually gets to do the math, the real number crunching. And yeah, these should look pretty familiar to you. Add does exactly what you think. It adds a value to whatever we have on our accumulator scratch pad. Sub subtracts from it, and inc is just a nice little shortcut for incrementing or adding one. It's simple, it's direct, and it's incredibly powerful. Okay, but this is where things get really interesting, because a program isn't just a shopping list of commands you follow from top to bottom. No way. It has to be smart. It has to make decisions, repeat things, and change its path based on what's happening. And that's where jumps and comparisons come into play. And the key thing to get here is the difference between a dumb command and a smart choice. JMP, or jump, is unconditional. It's like saying, go to this line of code, period, no questions asked. But JZ, jump if zero, now that's conditional. It says, hey, if this condition is true, then you can jump. And how do you check the condition? With CMP, or compare. And I'm not exaggerating here, this simple little combo, compare two things and then maybe jump, is the fundamental building block of all decision-making in pretty much every computer program ever. So, okay, we've written our code using these nice human-friendly mnemonics. We have a text file. But how does that text file become the actual ones and zeros that the processor can understand? What's the next step? Well, for that, we need another piece of software. It's called an assembler, and its job is basically twofold. First, it acts like a proofreader, scanning our code for any typos or mistakes, making sure we used valid commands. But then it does the really heavy lifting. It translates every single one of our mnemonics into the right string of ones and zeros. Now here's a really clever bit about how this works. most assemblers actually read your code twice. And you might be wondering, why? Well, think about it. You might write a command that says jump to the end, but the assembler hasn't even seen the end yet. So on its first pass, it just scans through the whole file and makes a map. It builds what's called a symbol table that just lists all your labels and where they are. Then, on the second pass, with that map in hand, it can do the real translation because it knows where everything is. Let's make this super concrete. Take a look at this piece of code. See those labels there, not found and found? Imagine the assembler is reading this for the first time. It gets to that instruction that says to jump to not found, but it has no idea where not found is yet. It hasn't gotten that far down the file.
And this is the solution. This is what the assembler builds during that first pass. It creates this simple little table. And now it knows, aha, not found is at address 100 and found is at 104. So on the second pass, when it sees that command, jump to not found, it just looks it up in the table, plugs in the number 100, and problem solved. It's really elegant.
Okay, so at this point, you might be thinking, wow, this seems really complicated. Why would anyone bother with this when we have modern programming languages? And that's a fair question. But here's the thing. Understanding assembly isn't just a history lesson. It's the absolute key to unlocking raw performance. I mean, when you need to squeeze out every single drop of speed, we're talking high-performance gaming, huge scientific simulations, nothing, and I mean nothing, beats assembly. It's also absolutely crucial for all those tiny little computers that run our world. You know, the chip in your car, your microwave, your smart thermostat. In the end, it's like this. Knowing a modern language is like following a recipe. But knowing assembly? That's like truly understanding the science of cooking. But of course, there's a trade-off. There's always a trade-off, right? And this quote really hits the nail on the head. To get that incredible level of control and speed, you have to write a lot more code. It really is the classic choice between raw power and modern convenience. So there you have it. We've pulled back the curtain and seen how our big, complicated ideas get translated step by step into the simple, powerful language of the machine. And this isn't just some dusty old concept. This is the literal foundation that all of our amazing modern software is built on. So I'll leave you with this question. Now that you know the computer's secret language, what would you tell it to do?